Hey, let's get started. So today we're going to be finishing up what we talked about yesterday with that marginal cost and marginal revenue problem, because the homework problem is very similar to that. Then we're going to get into volumes by slicing. And if we have time, which I know we won't, but if we have time, we'll get into volumes of revolution. Okay, so let's look at some announcements. Homework due Monday. You had homework due last night, and so I will post solutions to that today, and I will get that graded as quickly as possible, so that you guys can see what you did right, what you did wrong, and all that jazz. Okay. There's a discussion post. You should be able to talk about that post today. You'll have the background knowledge to be able to do what I asked you to do in that discussion post. You're just going to take a picture of something and upload it. Okay. So, questions? Okay, so here's where we left off yesterday. So we're selling cell phones, and we know we have a marginal cost function of C of x, that little c of x is 0.01x squared minus 3x plus 229, where x is the number of cell phones produced. And we have a marginal revenue function of little r of x is 429 minus 2x. If we want to find the area between these two graphs and the curve x equals 0, then that's just taking an integral. Yesterday we didn't find the top bound, but to find the top bound, I just set little c of x equal to little r of x. And that's what this work is over here. That's the weirdest arrow I've ever drawn. That's what this work is over here. Okay. If you go through and use the quadratic formula to solve that equation, you end up with x is either negative 100, but we're not buying cell phones, we're selling cell phones. So I throw that solution out, and the other solution is x is positive 200. Okay. So I'll give you guys a second to write that down. But this is the area we're trying to find. This integral represents that area. And the drawing's just the same as yesterday. It's the area between a straight line with a negative slope and a parabola that's opening up.
The one for the bottom half of the work you showed, if it was like to make one more product, that's where the work's coming from, the 1 plus or minus.
So where's the one coming from? Yeah, what about it?
Is that the one, isn't like that's how much it costs to make one additional product?
Oh, no. This is just me using the quadratic formula to solve this quadratic equation. So that's negative b. No, you're fine. Thank you for your questions. Any other questions? Okay, so when we plug everything into this integral, r of x and c of x, we end up with this. The integral from 0 to 200, 429 minus x, the marginal revenue function, is the top curve minus the bottom curve, the marginal cost function. And so we end up with this integral here. Okay, give everybody a second to copy that down. 1 Mississippi. 2 Mississippi. 4 Mississippi. Okay, so the rest from here is simplification, and then we'll have a philosophical discussion about what the area actually represents. So 429 minus 429 minus 229 is 200. So I'm going to have 200. So that cancels that and that. Minus 2x minus negative 3x. That's minus 2x plus 3x. So that's going to give me just plus x. So that's that. And then minus 0.01 x squared dx. Okay, so that's just me simplifying. I haven't integrated yet, right? Now, how do I take the integral of this?
Power rule.
Power rule, exactly. I take this piece by piece, term by term, and just use the power rule at every step. So the integral of 200 is 200x, perfect. Plus the integral of x, well, the power rule tells me that that's what? X squared over 2, perfect. And minus 0.01 x squared. What does the power rule tell me here? Well, the 0.01 is just a constant. It's going to come along for the ride. Will, what were you going to say?
0.01 x cubed over 3.
Perfect. Exactly right. Then I'm going to plug in 200 and 0 and take a difference. But notice when I plug in 0, I just get 0 in all of those, right? So really, I just care about what happens when I plug in 200. So I'm going to get 200 times 200. Well, that's 200 squared plus 200 squared over 2. A little gunky this morning. Minus 0.01 over 3 times 200 cubed. Let me write that times a little better. So let me type this into a calculator. 200 squared plus 200 squared divided by 2 minus 0.01 divided by 3 times 200 cubed. And that gives me $33,333.30 units and 0.33 units. So this is 33,333.33. You round to the nearest hundredth for whatever reason. Okay, so any questions about any of those steps? These applied problems I find are really, once you figure out, once you wade through all the lingo and figuring out what words mean what, the applied problems are really pretty easy once you are able to wade through that. Just setting it up is the hard part, but this integral was actually fairly simple to do. It's just 3 power rules in a row, right? So this tells me that if I draw, let me draw the area that we were interested in. Add page. If we draw the area that we were looking at, or sketch it very roughly, like I did yesterday. Well, here's that this is for 29 minus whatever, minus 2x. And then here was that 229 plus 3x minus 0.01, or plus 0.01 plus 3x plus 0.01x squared. So we just found this area here. What does that area represent? Well, let's think about what we integrated. Remember that the marginal cost function that we integrated, that's really, oops, marginal cost function is really the derivative of just the cost function, right? So we integrated the marginal cost and the marginal revenue. Let me move this. We integrated this, right? This is what we integrated. So when I integrate this, just with, for a second, looking at an indefinite integral, what do I get? If I integrate r prime minus c prime, what? Exactly, that just undoes the differentiation, right? And so that should leave me with capital R of x minus c of x, and I'm ignoring the constants for a second. Okay, so just the indefinite integral gives me what? What is revenue minus cost? Profit. That's exactly right. This is the profit for any, if this tells me the profit for if I'm selling X cell phones. Profit if I sell X phones. Okay. So now looking at this graph, we integrated from 0 to this point where the curves intersect. Okay. So what does that mean? What if we had integrated from here, or sorry, from 0 to this point here, where the curves switch, where then the marginal cost is actually bigger than the marginal revenue? Would that be bigger or smaller? And forget about an actual area bounded by a region. I integrate and I get a profit. So when I integrate up to here, I get $33,333.33. What if instead, so that's if I sell 200 cell phones, because we integrate from 0 to 200, I make that much profit. What if we had instead integrated R prime minus C prime, no switching of the variables, up to say 201? Well, up to here, R prime is on bottom, C prime is the top curve. So what would that integral give me between 200 and say just 201? Would it be positive or negative?
It would be a loss, I guess.
Yeah, exactly. If I integrate R prime minus C prime, where C is bigger than, or sorry, C prime is bigger than R prime, that's going to give me a negative number there. Again, I'm not really talking about actual areas right now. I'm just talking about integrating R prime minus C prime. So if I had integrated to 201, or in other words, if we had looked at selling 201 cell phones, I would have made less profit. What if I had only integrated up till say 199 cell phones? Well, would this number, the number that I got, would that be bigger or smaller than the integral from 0 to 200? So instead of going all the blue area, I get the red area. Is the red area bigger or smaller than the blue area? Smaller. Okay, so if I had only integrated up to 199, I would have gotten a smaller area. If I had integrated to 201, I would have gotten a smaller number, not really an area. So what does that tell me about the number 200, integrating from 0 to 200? Yeah, exactly. This represents the maximum profit, right? And this is actually something, if I gave you the revenue function and the cost function, I asked you find the maximum profit, what would you do? You took Calc 1, you would take the derivative and set it equal to 0. Well, now I just gave you the derivatives. We set them equal to each other, which is the same thing as taking R prime minus C prime and setting it equal to 0. And then we integrate to find the maximum profit. Okay, so this integral, this area under, or between these curves, that's bounded by those curves until they intersect, that represents the maximum profit that we can make. Okay, does that make sense to everybody? Do we have any questions on revenue, cost, marginal revenue, marginal cost?
So that process, I just want to clarify. It's like you take the derivative and then you and then you subtract them, and then you take the integral of the.
So to be clear though, we started with the derivative, and that's actually in real life. Normally, you don't just know your cost function right away, but you can increase your production by 1 and see how your cost is affected. And so normally it's easier to get the marginal cost and the marginal revenue in real life. And so we started with the derivatives, set that equal to 0 essentially, and then integrated to find our maximum profit. Exactly right. Any other questions? Very good. All right, so with that, we're going to get into volumes by slicing. Okay, so this and volumes of revolution are two applications of integration that I really wanted you to see before we start just digging into techniques of integration, because I find techniques of integration interesting, but I understand some people don't. And so keeping the applications in mind, I think is helpful. Okay, so this is another application of integration is finding volumes if you know the cross-sectional area of some shape. For instance, this coffee cup is just a cup, right? If I take slices, if I were to cut this in half, first of all, coffee would spill everywhere. But if I were to cut that in half and I held the cut to you, what would it look like? A circle, right? And no matter where I cut this, when I look at the cross section that I get, it would be a circle. This is a shape that has cross sections that are all circles if you cut parallel to the base. Okay, your iPad, it's very thin, but if you cut this way, what would you get if you cut your iPad across that way? You'd have to pay a lot of money to the IC. I don't know who you would pay, but you would also get cross sections that are very, very thin rectangles, right? A lot of things in real life can be represented pretty closely by this process or these shapes that have a constant cross-sectional shape. Okay, so let's look at a very easy one, very similar to the coffee cup. Let's look at finding the volume of a right circular cylinder with a radius r equals 3 and a height of 10. Okay, so a right circular cylinder, if anyone doesn't know, is a shape that looks like, a Coke can, or a cola can, rather. I don't play favorites. So here's what we're looking at. We're looking at this shape. It's got a radius. The top and bottom circles have the same radius of 3, and it has a height of 10. Just units, whatever units you want. Okay. As long as the units represent one. So this is the shape we're going to find the volume of. Using what I'm about to show you is a little bit overkill. You might be able to see right away what the volume is. If you think of this as just a circle that you sort of stretch out. But I'm going to show you the process that's going to work in general. Okay. So if we take cross sections of this shape, again, we're just going to get circles. And with the coffee cup, when I cut, I get circles of different sizes. With this cylinder, when I cut this thing parallel to the base, every circle is the same shape and size, right? So when I take cuts of this cylinder parallel to the base, I get cross sections that are all circles of radius 3, right? Radius r equals 3. So again, that's me. I'm taking it just a general cross section. And that's the shape that I get, that dotted little shape there. So let's look at this method. We're going to, again, be using Riemann sums, okay? So the whole idea behind using Riemann sums for this is the following. Let's look at my shape. I have my right circular cylinder here. Oops. And the whole idea is I'm going to cut it up. I don't know how to find the volume of that, allegedly. But I'm going to cut this up. This is r equals 3, and this is, gosh dang it. This is 10. There we go. I'm going to cut this up into 1,000 pieces. Okay. Now for us, each piece is going to be a very thin. I'm going to look at what happens if I cut this like this. So I'm going to take this little sliver of this thing. Okay, when I take this little sliver and I'm cutting this perpendicular to the height, right? So I'm gonna take a little sliver where the width of this sliver, I'll call it delta H. Okay. So I cut it and then I pull that sliver out and I examine just what is the volume of this little sliver. That's my wrapper name, by the way, little sliver. So yeah, so delta H, we know the width of that is delta H. We know the radius of this is 3. Okay. So what would you guys say the volume of this coin shape is? Exactly. We have pi r squared. So it's going to be essentially the area of that circle just times the height, right? And so you can see why this method is overkill, because why not just do that for the whole cylinder? But stay with me. So I'm going to get pi times r is 3 squared times delta H. That's the volume of this little sliver of the big cylinder, okay? So I'm going to call that dV for a second. A little bit of volume, or delta V if you want, who cares? So that was for a tiny little sliver. So then the volume is approximately, the volume of the whole thing is approximately, well, I'm going to add up, if I have n of these slivers, I'm going to add them all up, right? This is the whole process of Riemann sums. So there's no i's happening here because everything's constant, but I can still use the summation notation. 3 squared is 9, fun fact. So I'm going to get 9 pi delta H. So now we can think of this of delta H as, well, I have a length of 10. I'm using delta H 10. I'm using in rectangles. So delta H is 10 over n, right?
Could you repeat that?
Yeah. So delta H, how many little slices am I taking? Well, I've got a whole big height of 10. I'm using n of these slices. Where n, we're going to let go off to infinity. Again, here it doesn't matter, but in general it will. But to find delta H then, how many or how big do my slices need to be? Well, I take the big length of 10, divide it by the number of rectangles, or not rectangles, sorry, the number of slivers I'm using. That's how big delta H needs to be. Okay. I is going to be in general, if I look at, let me add a page. In general, we're going to be looking at shapes that have non-constant cross sections, but they'll all be circles. So in general, I'm going to be taking shapes that the slice that I'm looking at, the radius will depend on which slice I'm looking at. But right now, this example is so simple that it really doesn't depend on what slice I'm looking at. But the idea is still the same. I'm going to get true equality. This is a Riemann sum. It's one of the simplest Riemann sums we've ever looked at, but it is a Riemann sum where f of x is just 9 pi. F of x is the constant function 9 pi. Okay, so I'm going to get the limit as n goes to infinity of the sum I equals 1 to n of 9 pi delta H. Delta H. Well, this is, again, this is f of x. The interval that we're looking at is h is between 0 and 10, right? So this is really just the integral from 0, h goes from 0 to 10 of 9 pi dh. Okay. And if you do that integral, 9 pi is just a constant. So you're going to get 90 times pi, which it makes sense. It's just pi r squared times the height. Okay. But this process of taking slices, looking at one individual slice, that will in general depend on which slice you're looking at. And then adding all those slices up is still going to work the exact same way every time. Okay. So the answer here is 90 pi. Okay. So let's look at a slightly more complicated example. Sometimes the easy examples are so easy that it makes it hard. Let's look at a slightly more complicated example where you actually do need to worry about which slice you're looking at. Okay. So let's look at finding the volume of a pyramid with a square base. Okay. So I've already drawn this pyramid for you. Here's a pyramid with a square base. This square base, each of the sides has a length of 4, and the pyramid is 5 units high or tall. Okay. So we want to find, for the first thing we're going to do, if you have a volume by slicing problem, the first thing you always want to do is figure out, you're either going to be told how to take the cross sections, or you need to find out how to take the cross sections so that all the cross sections will have a shape that you know how to find the volume of. Okay. So when I'm taking cross sections of this pyramid, I have several options. I could take cross sections that are vertical. So maybe a cross section like this. And when you do that, maybe you'll get something that looks like that, this weird rectangle shape. That's going to be hard to do. You could do it, but the thing is, once you cut this pyramid in half, then all of a sudden that rectangle turns into a triangle, and you have to do a weird little workaround there. That's annoying. I'm not going to do that. But it is possible to take cross sections using vertical slices like that. We could take horizontal slices. What would horizontal slices look like? Or in other words, slices parallel to the base. Yeah, those cross sections would all be squares, right? So if I cut this pyramid, parallel to its base, I would end up with a cross section that looks like this. Okay, I would end up with a cross section that looks like a square. It's definitely a smaller square than the actual base of the pyramid, but it's a square. And squares, I know how to work with. Okay, so we're going to look at taking cross sections of this thing parallel to the base, because those cross sections are going to give us squares. Okay. So our job then is to find out this volume. Again, we're going to use volumes by slicing. So let me erase the actual plane here. So let's, instead of looking at this pyramid as one continuous thing, let's cut it up into slices. Here's one slice that we would get. And then another slice could be like this. And then another slice like this, and so on, right? big slices. Okay, think of using just rectangular pieces of wood to approximate this pyramid. Okay. So let's look at this slice that I first drew, the slice in the middle. What should we call its width? Its width looks like that we're going to take equal slices. So each slice will have a width of, well, I'm building up the height. So I'll call the width delta H. Okay, delta H again. It's not always going to be building up the height, but here we are. Okay. So then if I can just find the side length, then I'm good. Then I can find the volume of this little sliver of the pyramid. I can add all of the pyramid slivers up, and then I have the final solution. Okay, so I'm going to look at this pyramid again, a little simplified, so that we can really see what's happening. There's that drawing there. Okay, so we're looking at this slice here that we'll say is a length of H from the top. Okay. And to clean things up even more, I'm just going to, instead of drawing the full sliver, I'm just going to draw the top of the square. Okay, so here's the top of that sliver, that square though. Okay, so that length from the tippy top of the pyramid to the top of our square is H. Okay. So then how do I find the side length associated with that square? Who knows? With pyramids, there's almost always one method that you're going to use. No, you're fine. How do I find the side length? This length here. How do I find that side length? Because that's what we need. I need to find that side length using the properties of this pyramid somehow. And again, with pyramids, there's almost always one thing that you're gonna do. Does anyone maybe know off the top of your head? If not, that's totally okay. It's good question. It's going to be related to it, but it's not just 4 because this one's shorter, right? But it's definitely going to be related. So with pyramids, the way pyramids are built, you're almost always going to use similar triangles. Okay, so let's look at just one face of this pyramid. Okay, so here's the bottom. This length right here is the bottom of our pyramid, and that's got a length of 4, right? So this is us standing on one side of the pyramid. This tippy top up here, this length isn't 5. We can find that length pretty easily. We'll do that in a second. But we can find that length, but it's not 5 because that tilts away from us, okay? But then this line right here, which I'll color in red, this line right here, well, that's going to look like about right there, right? I don't know the length of that line, but we can use similar triangles to find out. Okay. And the way we can do that is if we know the length of that dotted vertical line, then we're golden. Then I can use the same process to find the red line And we're good, okay? So the only thing we need to know is what is the length of that dotted line? And who can say? Does anyone know how to find that? It's not 5. Yeah. No, you're good. Yes, exactly. We're going to use the Pythagorean theorem because the pyramid, if we look at this drawing here, well, that dotted line, let me draw it in blue over here. That dotted line is that line right there. Well, that length right there, what's that solid blue line? What length does that have? That's from the middle of the square to the middle of the side length of the base closest to us. What length is that? 2, right? It's half of the side length of the square. So this blue line has a length of 2. The line from the tippy top of the pyramid to the middle of the base of the pyramid, what length does that have? That has a length of 5. So then how do I find the dotted blue line?
Pythagorean theorem.
Pythagorean theorem, exactly. And so the Pythagorean theorem tells me that this dotted blue line here has a length of, well, the square root of 2 squared, which is 4, plus 5 squared. So it has the length of square root of 29. Okay. So we have the dotted line, the dashed line is the square root of 29. And now we have, we want to find the red line, right? So we're going to use similar triangles. So I'll call this red line, for now, I'll call that side length R. If I know the length of just that line, then I can find out what R is, right? So how do I find out the length of that line? Well, we can do the same thing, but pretend that we're just looking at this square as our base now, right? Because this height here is h. If that height there is, the height from there to there is h. Okay, so that means that if the full length of the square that we care about, if we're calling that r, then the length here from the middle of the square that we care about to the edge of the pyramid, that's r over 2, right? Again, take the length of the square, divide it by 2. So then the length of that slant is the square root of, well, we're calling that h, so that's h squared plus r over 2 squared. Questions so far? Why is it the same reason that this was a 2 down here and not a 4. Because if I'm calling the whole red line r, then the length from the middle of that square to the edge is r over 2. Okay. So, question. Okay, so then we have we want to get that length in terms of h. Okay. We want that red line in terms of h. Well, that means that I can just solve this equation that I get using similar triangles in turn, solve that R in terms of H, okay? So when I do that, using similar triangles, well, the height over the base of the big triangle should be the height over the base of the small triangle. Okay, that's similar triangles for you. So the square root of 29 over 4, that's going to be the square root of h squared plus r over 2 squared over r. So that's, again, vertical over horizontal for both triangles. Okay. These numbers are not working out the way I remembered them, so I'm sorry about that. But now I have one equation involving r and h. And again, if I can write r in terms of only h, then we can integrate and we're done. Okay, so what is r in terms of h? Well, how do I solve this equation for r? First thing I want to do is square both sides. So when I do that, when I square the left-hand side, I'm going to get 29 over the square root of 29 squared is 29, and then 4 squared is 16. When I square the right-hand side, well, when I square a square root, I get the thing that's under the square root. So I'm going to get h squared plus r squared, r over 2 squared. I'm going to write that as r squared over 4. And then when I square the bottom, r squared is just r squared. So then the rest of this is solving for r, and really what I'm interested in is solving for r squared, right? Because the red line is the length of that. So if I want the volume of that sliver, that's r squared delta h, right? So really, if I can solve for r squared, then we're good. All right, so let's move r squared over here, multiply both sides by r squared. I get 29 over 16 r squared is equal to h squared plus r squared over 4. Then I'll subtract r squared over 4 from both sides. So I'll get 29 over 16 minus 1/4 r squared is equal to h squared. And then 29 over 16 minus 1/4, well, a common denominator there of 16, so 29 minus 16 over 16 r squared is equal to h squared. Four. Oh, thank you. Sorry, my bad. Thank you very much. Minus 4. And so that gives me 25 over 16 r squared is equal to h squared. So that r squared is 16 over 25 h squared. Or in other words, again, this is really what we need. But in other words, r is 4, take a square root of both sides, 4 over 5 h. So, what time is it? Okay, we still have time. All right, so we can go back to our drawing. We had a sliver that had a width of delta h. And we called this length here r. We didn't know how to find it at first. Then we used similar triangles. There are probably similar triangles that you could have used looking at that solution. But we got there. We got that r is 4 over 5 h. Okay. So then what is the volume of this little sliver just in terms of H? B equals. Well, it's the same way with the coin shape. You just take the area of one of the bases and multiply by the height, right? So what's the area of the base? Yeah, 4/5 H, all that squared, very good. And then I multiply by that little bit of height there. Okay, so I'll call this again dV, because this isn't the full volume, this is a little bit of volume. Okay. So then I'm going to take a sum of all of this stuff, right? The full volume is going to be really approximately for right now, is going to be the sum of 4/5 HI, and HI is going to be how many steps I've taken. Sorry, we're looking at H from the top. HI is how many steps I've taken from the top. So HI is that length. Okay. 4/5 HI squared delta H, where I is 1 to n. And so to make this exactly equal, I'm going to take a limit as n goes to infinity. And when you do that, you end up with, well, this is a Riemann sum. Now this is f of h, right? So I get 4/5 h squared. Delta h turns into dh. And h started at the very top. The HI start at the very top and go to the very bottom. So when h is 0, we're at the tippy top. What does the bottom correspond to? H equals
Would it be 5 for the height?
5. Exactly right. H is 5, the height. H equals 5. Very good. And so we can evaluate this integral. This is, if I square everything, this is 16/25. That's the integral from 0 to 5 of h squared dh. And now I take the integral. I use the power rule. So this is 16/25 times h cubed over 3. I plug in 5, I plug in 0, which is 16/25 times 5 cubed over 3. When I plug in 0, I get nothing. So 5 cubed over 5 squared just leaves me with 5, like that. And so that's 16 times 5, which is 80/3. Now, there's an easier way to do all that. There's a sort of a shortcut that we're going to look at in a second, where you don't have to look at actual Riemann sums that most people prefer to look at. But are there any questions about this pyramid problem? There's a pyramid problem on the homework. The similar triangles, figuring out the easiest ones to use is hard sometimes, but it's just similar triangles that you need to use to figure out the length of a square, or actually in the homework problem, it's actually a triangular base. Okay, so on the homework problem, you're going to follow a very similar path to get to that answer. So this is volumes by slicing. They're not all this bad. That one, the numbers were kind of bad, I acknowledge, but they're not all this bad. In general, to do a volume by slicing problem, and this is what I'm going to pick up tomorrow, but I'm going to show you the steps really quick. You examine the solid of interest that you're trying to find the volume of, and you determine the shape of a cross section of that object. Either I tell you what cross sections to take, I'll say perpendicular to the XY plane or something, or you need to figure out what cross sections you need to take. Okay, you're always going to make drawings at step number 1. Draw the solid, draw what the cross sections look like. Okay. Step 2, you're going to determine a formula for that cross-sectional area, or for us, we look at the volume when you multiply it by delta H. Okay. And then step 3, you integrate. Really, all we did, if you think about it, we found the area of one of the bases, and then we integrated, and that's it. You integrate over the appropriate interval. Okay, so we're going to simplify this a little tomorrow to see how to apply this to different problems. Okay, so tomorrow we're going to look at this shape and figure out how to find the volume. It's it's the Sydney Opera House-esque, how to find the volume underneath the roof of that building there. Okay, so you guys have what you need to be able to do a lot of the homework, so make sure to get started on the homework. If you run into any questions, let me know, and I'm more than willing to help you out on anything. And then other than that, feel free to have a great day, and I'll see you guys tomorrow.
Thank you.
Thank you.